guys, welcome back to the last video in our series on engineering physics option and IB. This one is very short. As a matter of fact, I could probably just get you guys to read it and you'd have no problems figuring this part out by yourself. But it's basically talking about what we talked about in terms of resonance in physics 20. Covered it in waves, sort of, but there's just some different terms involved. It'd be very short. So here we go. Forced vibrations and resonance. So, as we learned in physics 20, when something is disturbed and left to oscillate without further interference, it's said to oscillate at its natural frequency of vibration. So we called that, in physics 20, it's a different term. We said it was its resonant frequency. That's what we mean by that. We don't use resonant frequency here in IB, natural frequency of vibration, symbolized by F0. Okay, so if you, like, I don't know, put a ruler on the edge of a counter and you put your hand over one end and you twang it, or a guitar string or something like that, it'll eventually stop vibrating. So that's called damping. Damping is the dissipation of the energy of an oscillator due to resistive forces. So damping can be very light. The oscillator may take some time to dissipate its energy. So, I don't know, a guitar string can ring out for a while. Examples of underdamped systems include a pendulum and a mass oscillating the end of the spring. So if you have a pendulum, like the ones we work with in the lab in, again, physics 20, where back and forth, it takes a while for it to stop. So you would call that underdamped. Overdamping occurs when there are considerable frictional forces. So the decrease in amplitude with time is often exponential. An example of an overdamped system would be a pendulum in very heavy oil, so it might not even make one oscillation before it stops. Critical damping occurs when vibrations are unhelpful or dangerous, so oscillations are stopped extremely quickly, so on purpose. Examples include shock absorbers or in self-closing doors. Okay, so pushing a kid on a swing. Talked about this as resonance. A forced oscillation occurs when a regularly changing external force is applied to a system, resulting in the system vibrating at the same frequency as the force. So, pushing a kid on a swing. Resonance is the increase in amplitude and energy of an oscillation when an external oscillating force has the same frequency as the natural frequency or resonant frequency of the system. So we called that forced frequency. Resonance occurs when the forced frequency matches the natural resonant frequency, or again, the natural frequency here in IB. So here we've got a graph. It's called it's a frequency response curve. So as you approach the forced or driving frequency, gets closer and closer and closer to the natural frequency, the amplitude gets higher and higher. So if you time your pushes correctly with the natural resonant frequency, like say of a kid on a swing or something like that, the kid's going to get higher and higher. If you just kind of miss as the kid's maybe just moving away, then you push, or coming back and then you push, you're still going to have resonance, but it's not going to be as great as an amplitude. So Q factor. Q factor is what we use. It's a number to represent the amount of damping quantitatively, assigning a number to it. So as it says, Q, or quality factor of an oscillator, is a way of representing the degree of damping. So you can see that the lower the Q factor, the more it's damped. So a high Q factor means that there is little damping. So here's very simple formula. Q equals 2 pi energy stored divided by the energy dissipated per cycle. And for a resonating system that's oscillating steadily, Q factor is 2 times the resonant frequency times energy stored divided by power loss. It's very simple formulas, like you'll see in your practice questions, that notice there's 1, 2, 3 variables in here and 1, 2, 3, 4 variables in there. So it'll be very typical kind of word problems that you're very much used to by now. Okay, and you do have to know about some useful effects of resonance and some maybe harmful effects of resonance. They're listed in your book. I've decided to list them here as well. So, useful effects like the natural greenhouse effect. Um, Molecules in the atmosphere absorb radiation, warm up the atmosphere to where life on Earth is a little bit more hospitable. Radios and TVs are tuned by changing the frequency of an electronic circuit until it matches the driving frequency of a signal. Quartz crystals resonating in electronics as timing devices. Sounds from musical instruments. And MRI machines. We talked about that in the imaging section. Radio waves of the right frequency are used to change the spin of protons, in other words, the hydrogen nuclei in water molecules. So many different useful effects of resonance. Harmful effects of resonance include things like parts of machines or engines can vibrate at certain frequencies. You don't want that. Obviously, earthquakes can affect some buildings more than others, and strong winds or currents can cause dangerous resonance in bridges or towers. And that's the end. That is the end of forced vibrations and resonance. So, very, very quick little section. Not a lot there. So, read pages 582 to 587, and then do the handout, practice problems. That's it. See ya.